Hi there, and welcome to our video on infinite limits. This will be our last video before the first quiz, quiz, quest, test, however you want to think of it. It's going to be the quiz at the end of chapter 1. So along with this, you'll also want to spend some time between our next class and the day of the quiz, looking over the review stuff too. So. Our lesson objectives for this particular video is number 1, to determine infinite limits from the left and from the right. And then the second one, find and sketch the vertical asymptotes of the graph of a function. So some of that stuff I think you're pretty familiar with. I've seen you sketch, all of you sketch vertical asymptotes in a graph of a function before, so this should be nothing really new, except for maybe the limit part. So we'll look at that. First, let's explore a function f of x equals 1 over x minus 2. Okay, the x minus 2 is in the denominator. So what we're going to do is we're going to look at the behavior of what's happening to that function as we move closer and closer to 2. So I have a table. What you see is a table here. Again, this table should look familiar. You dealt with something similar to that before. The top row are x values. The bottom row is the function values. Notice a question mark at 2. Okay, in fact, this function is not defined at 2 because when you put 2 in for x, you get a 0 in the denominator. So what we're looking at here is trying to determine what happens to the function values as we move closer and closer to 2. So let's start from the left. When I put in 1.9 in for x, I'm going to get a negative 10. When I put in 1.99, I get a negative 100. I put in 1.999, so I'm really, really close to 2. I'm getting something very big, negative 1,000. If I even move closer, you kind of get the idea, you're going to get something even bigger. So what happens here, I can say that the limit in this case, as x goes towards 2 from the left, that's what that negative sign, remember that negative sign means that, of f of x comes out to be that it's going to negative infinity. We're just getting big numbers in the negative direction as we keep moving closer and closer to 2. Let's look at what happens when we come from the right. 2.1 I get 10, 2.01 I get 100, 2.001 I get 1,000. You kind of get the idea that if I went to 2.0001, I'd get something even bigger. I'd get 10,000. And so as we move towards 2 from the right, what you find is that the function values are getting very, very big in the positive direction. And so in this case, we would say that the limit as x approaches 2 from the right of f of x would be positive infinity. Now we get to the definition of an infinite limit. This is in your book, so you could look at that as well, but I'll read it through and you'll want to get this down in your notes, and then we'll talk about what that means. We're going to let f be a function that is defined at every real number in some open interval containing c, except possibly at c. Okay. Then the limit as x approaches c of f of x equals infinity means that for each m greater than 0, there is a delta greater than 0 such that if my function value is greater than m, that I know that the value that I'm plugging in is within delta units of c. So I know that the absolute value of x minus c would be less than delta. So in other words, as I pick values that are going to be even closer to c than delta units, I'm going to get something much bigger than m. And that's what it means. That's what happens when you go off to infinity. Let's look at the limit as x approaches c for negative infinity. The limit as x approaches c of f of x equals negative infinity means that for each number n less than 0, there is a delta greater than 0, such that if f of x is less than, it should be n. Let me get that written as an n. Then the absolute value of x minus c is going to be less than delta. So look at that again, read it over, and then get a copy down, and then we'll take a look and kind of give you a look graphically at what this means. Let's look at what it graphically meant in terms of that first part, that the limit is equal to, goes off to infinity, positive infinity. Remember what it said is that if the limit as x approaches c of f(x) equals was going towards positive infinity, then there was a positive number m such that if x was within delta units of c, that the function values will be greater than m. So what you see here on this graph, you'll see that at this, the red line is a vertical asymptote at c. You'll see the c labeled there. You'll notice that these here are delta units. I've labeled m here, and so I've graphed a function f of x on both sides that go up, keep getting closer and closer to c. As we get closer and closer to c, it's shooting up. Okay, so you can get the idea. We have this vertical asymptote. I've drawn in m, and what I want you to notice, what that definition says, is that if I pick any value that is within delta units of c, so if I pick anything in this interval here, between the two kind of like tan or brownish lines, if I pick any value and I plug it in besides c, if I plug it in, I'm going to go up, I'm going to hit the curve at this point, and I'm going to come across, and I will get, my function value is going to be greater than m. And no matter what value, when you have a vertical asymptote, no matter what value you pick for m, you can always go through and find, you can always move closer to c, and you're going to get something that's going to be bigger, because we're always moving closer and closer to that vertical asymptote. We're just never reaching it. So that's really kind of a graphical look at what that definition of an infinite limit looks like. Now, in terms of vertical asymptotes, if f of x approaches infinity or negative infinity as x approaches c from either the left or the right side. So now notice what this is saying. All you have to do is from one side you have to be going off to infinity. Doesn't matter what's happening to the other. If from one side you're going off to infinity or negative infinity, then you know you have a vertical asymptote at x equals c. Okay. So we're going to let h of x equal f of x over g of x such that f of x and g of x are continuous on AB. And we're going to let c be an element of AB. So c is some number in AB. If f of c does not equal 0 and g of c equals 0, then there exists an open interval containing c such that g of x is not equal to 0 for all x not equal to c. Then we know that h of x here has a vertical asymptote at x equals c. Okay. So, in other words, if I go and look at a function, if I have a function h of x, and it's a rational function, and I know that there's a spot where that I can plug in for a value in for x in function g, and that will give me 0. Okay, as long as that's not part of a long stretch of zeros down there, that would mean we have a vertical asymptote. That's what this part here is saying. If there exists an open interval containing c such that g of x does not equal 0 for all x and c, that's not equal for all x not equal to c. What that's saying is that we're not just looking at a stretch of x values for which that denominator would be 0. We just have one particular one. So then we know we have a vertical asymptote at x equals c. Let's look at a problem here. We're going to let f of x equal 3x over x plus 1. And what we want to do is we want to find the limit as x approaches negative 1 from the left and then from the right. Now the first thing I want you to notice on this one is that if we take it back to what we had before in the definition that we just looked at, this denominator here would represent g of x. And I want you to notice that there is only one specific x value that's going to make that denominator equal to 0. And that value happens to be negative 1. There's no other value. You know, it's not going to be 0. We're not going to come up with an interval of values that will make this 0. There is just one specific one. And that's the important part of that definition. Okay, you have to have it that the function's defined at every other place except for at that particular c in that small interval. So that in order to have the vertical asymptote. So we have that condition that exists here. Let's take a look. What I'd like you to do now is I would like you to pause the video and I want you to determine what happens as x approaches -1 from the left and from the right. Once you have that, come back and we'll talk about we'll check your work and talk about what should have happened if you made a mistake. Okay, welcome back. In this case right here, when I have the limit as x approaches -1 from the left of f of x, in this case, I'm putting numbers that are smaller than -1, okay, or to the left of -1 in for x. So when I do that, when I put numbers, -1, something coming from the left, so I have numbers that are farther away from 0, but they're negative. I'm going to get, in my numerator, when I put those numbers in for x, I'm going to get a negative. And here, because I'm putting in things like -2, -1.1, -1.01, -1.001, I'm getting those values I'm plugging in, when I add 1 to them, are going to end up being, negative. And so, in this case, what I have is when I go from -1 from the left, I'm going to get a negative or a negative, and I'm going to be going towards a positive infinity. When I go from -1 from the right, so now what we're putting in are numbers that are like -0.9, -0.99, -0.999. In that situation, my numerator is still going to be negative, but my denominator is now going to be positive. And so in that situation, but we're going to keep that denominator still going to be going closer and closer to 0. I am going to be going off towards negative infinity. And so the question we have here, does f of x have a vertical asymptote at x equals -1? Well, the answer on this one is yes, it does. Because remember, no matter what, if we're going from, as we approach from one direction, if we're going towards infinity or negative infinity, we do have a vertical asymptote. So in this case, yes, there is a vertical asymptote there. Let's take a look at a second function. In this case, we have a piecewise function, g of x, is going to equal 2x plus 1, and we're going to use that piece when x is less than or equal to 1. And g of x is equal to 2 over x minus 1, and we're going to use that piece when x is greater than 1. And so what I'd like you to do is pause the video, and I'd like you to go and determine the limit as x approaches 1 from the left and from the right for g of x. Welcome back. Now, in this case, we want to find the limit as x approaches 1 from the left first in the first piece. So what you have to remember on that is that because we're using numbers from the left, we're putting in numbers that are less than 1. And so what we're looking at, the values that are less than 1 end up going in this top piece. And as we keep moving closer and closer to 1, remember we can just do a substitution in this one, and we can see that that limit as x gets closer and closer to 1, from the left, it is going to equal 3. Now, as x gets closer to 1 from the right, because we're looking at values that are bigger than 1, from the right is bigger than 1, we're going to use this bottom piece here, the 2 over x minus 1. And so, as we get closer and closer to 1, we're putting in numbers bigger than 1, but very, very close to 1. So 1.1, 1.01, 1.001, 1.00001, and we can keep going that way. And I take 2 over those. Well, that means the denominator is, as x gets closer to 1, the denominator is getting closer and closer to 0, but it's still going to be positive. And so when I take the reciprocal of a positive number like that, a very small positive number is going to be a very big number. And so in this case, the limit as x approaches 1 from the right of g of x is going to be a positive infinity. And now we ask ourselves that same question. Does g of x have a vertical asymptote at x equals 1? And in this case, the answer is again, yes, it does. Because, remember, the only thing that was required to have a vertical asymptote was that you had to be approaching, as the limit as x approaches c of the function had to be approaching infinity or negative infinity from either direction. It didn't have to be from both. It just had to be from either direction. So if just one of them went towards positive infinity or negative infinity, you had a vertical asymptote. This now concludes the video on the vertical asymptotes. And with that, we'll see you in our next class.